this is, so the whole mechanical engineering is just convection, thermal convection is just this equation. And you can have the source here, huh? Sometimes you have the source, so you can have the source here, okay? Yes, X, Y, Z, and T. Of course, with the source, the system will be very complicated. I mean, you have a cavity, for example, you make the temperature cavity increasing, and you connected a pump to that, huh? And send some heat from some other source to that. Or you make it some fire. So the situation will be complicated. But this is a question. I'm not interested to talk about the source because I don't know the form of the source. This is very clear, that time difference. But this is my motivation because I can use this identity, huh? Divergence F gradient, and develop that. So divergence, you know, in terms of divergence gradient T is plus partial derivative of this. This is a source. So this is the Fourier law. Fourier law for the heat. Okay, I don't want to solve this equation. So one of the future lecture will be to solve such equation like that. This is called the second order partial differential equations. And sometimes it's very hard to solve because you have a row here and row is not fixed number. So a row can be function of x, y, z. So this equation is very complicated. When we pass to the coordinate system, one of the strategy will be to solve like these equations. But let's look at that. We have a time derivative here also. That's very noisy. So that makes a lot of problems. Sometimes you can talk about the steady state system. Normally it happens when you have enough time to wait. If you wait enough time, I won't guarantee for you that the time derivative will be zero finally. But I don't enter the detail actually. But for our business now is that. This is what we know. I want to expand this equation. Divergence rho gradient T. Okay, this is like a vector for me, huh? And this is like a function. So I use this. Will be gradient F, gradient rho, dot gradient T plus rho divergence this vector. So you will have a gradient rho dot V you will have a gradient rho dot gradient T plus rho divergence gradient T. I don't know you get my point, you know. I started from df. With df I get one difficulty. I see something new appear, like gradient, huh? When I try to find the gradient for the combination of two, like that, I get a new object again. What is the color? Divergence, huh? And when I apply the definition of divergence to the real physical example, I get something else. Divergence gradient. Yes? So, using the vector analysis, differential vector analysis, differential calculus, vector calculus, you will get higher, lower. So, then the rest of the lecture, I want to talk about the divergence gradient. What is this? And maybe about the cross, but I'm not sure. So that's not the end of the story. So I want to tell you that sometimes in the real problems, you have a divergence gradient, divergence gradient, divergence function. You can have like that. So you can have del means this gradient, gradient, something. But this is the easy example which I prefer is this thermal. phenomenon. So I am looking to, I increased my level from the normal, and you know, before it was just dA, dx, you know, in the normal calculus. Normal calculus, multivariable. Multivariable gradient, operator. And operators comes to the higher level operators, like divergence. What is the divergence gradient T? Okay, I want again to use the notation. So divergence gradient T, huh? So this is a sigma I1 to 3 partial, what is that? Partiality. Yes, I use the definition of notation of the that. So that will be sigma I1 to 3 partial square T. Can I write that? This is called a Laplacian. So I told you that a wide range of the study in mathematical physics is about the solution of this equation, Laplace equation. Laplace equation is the most important equation in the whole physics, actually. For that reason, there is a branch of the applied mathematics called potential theory. So that's why I told you I can talk 2 semesters just about the solution of these equations in different areas. So this is, we call it Laplace operator. Laplace operator. Operator, of course, means that forget about what is written here. Anything, put it anything, we call it operator. And in modern literature, they call it Laplace-Beltrami. Italian mathematicians. Normally, Laplace operator, I use the Laplace, I prefer the Laplace. When your situation is not on the flat, I mean if your geometry changed to the non-Euclidean, not Euclidean, okay? The common word we use is the Beltrami because he was the geometrician person. So he was the person. I don't believe that. I think even the Laplace was aware that how to write this operator for the not flat space, non-flat space. But it's just we needed to respect to the name, the people. So let me to write this equation again, the heat equation. So after this note, I have this idea that I can write the heat transfer equation like that. I need to write in the better place. So gradient rho dot gradient T plus rho Laplacian T plus partial derivative is S. Heat transfer. This is a really interesting and very difficult equation in the elementary approach actually to solve. What is the question? The question is find the T. I will give you the geometry, and I will give you the temperature at beginning. For example, I say that the system started at temperature 30 degrees, for example, and give me the temperature after 1 hour in the other point, 1 meter from the source. This is a real question. For example, a volcano happens, so volcano, for example, or something, so explosion. You like the explosion happen, and then because this equation is exactly the equation we can use for the nuclear reactions. You know, this is anything. It's not. This is the way which I am thinking about theoretical physics, because you have a huge range of the phenomena, and you can describe all by just one equation. So this equation can be used for the neutron source. You have one neutron source, you put it here, and neutron started immediately for the decay. It sent the nuclear radiation to the ground. So